All right, in this video, we're going to go over Venn diagrams, and there's 3 learning targets. First one is you can explain what each number in a Venn diagram means in context. Secondly, you can construct a Venn diagram from a situation. And lastly, I can interpret and calculate probabilities when written in set notation. Before we get started, you may want to consider grabbing some colored highlighters or some colored pencils. We are going to be doing some coloring in this to help us see the intersections and unions just a little bit better. So whenever here, I've got 2 circles intersecting. This is called a Venn diagram. So we've surveyed a bunch of students and we've asked them where they've applied to college. We've got students that applied to UVA and we've got some that applied to tech. These are the results. So how do we read this? Let's start in the middle. This piece right here is where the 2 circles collide. This is the intersection. So this 5 right here means that there are 5 students in this survey who applied to both schools. Okay, so that is called the intersection. Let's look at UVA first. This entire circle right here, this large one, represents students who have applied to UVA in our survey. So as you can see, the 5 is included as well as the 15. So the 5 we know represents students who applied to UVA but also applied to tech. This 15 represents the students that only applied to UVA. So that means altogether 20 students applied to UVA. Okay, so same idea. We have UVA, tech. Got our same numbers. And we know automatically that we've got this intersection here, 5, which is how many students applied to both schools. So let's look at tech this time. Tech is this entire circle. So we know 5 of these students applied to tech, but they also applied to UVA. This number 3 is the number of students that applied to tech, but didn't apply to UVA. And this entire circle represents tech. That means that 8 students applied to tech. So the only number we haven't talked about is the 10 up here. This 10 on the outside represents this entire sample space, the rest of it. Since 10 falls outside of both circles, that means that 10 students in our survey applied to neither school. So that means that maybe they applied to different schools or maybe they didn't apply to school at all, but they definitely did not apply to UVA and they did not apply to tech. So in this particular example, notice how we don't have the circles intersecting, they're not crossing. So in this situation, we have 15 students applying to UVA. We have 5 students that are applying to tech. We have 10 students applying to neither. And because the two circles are not intersecting, we have 0 students applying to both. When you have a picture like this where the two circles are not intersecting, they have nothing in common, we call this mutually exclusive. When you have two events with nothing in common, we call them mutually exclusive events. So let's construct some Venn diagrams. So we have 100 students at Lake Braddock who were surveyed about return to school. Here are the results. We've got 25 students surveyed were seniors, 60 students surveyed plan to continue virtual learning, and 15 students are seniors who chose virtual learning. Our two events are we've got seniors and we've got virtual learning. In order to construct this, we want to work inside out. We want to know what that have in common and then work our way from there. So our bottom one tells us that 15 students are seniors who chose virtual learning. So the only place where seniors are virtual learning are right here in the middle. We know that 60 students surveyed plan to continue virtual learning. So virtual learning is this entire circle. And we know this entire circle should contain 60 students. But since we already accounted for 15, that means that we have 45 students who chose virtual learning but are not seniors. Now we have 25 students that were seniors. This entire circle represents seniors, and we've already accounted for 15 of them. So that means that there are 10 seniors in this survey who did not choose virtual learning. But wait a second, we surveyed 100 Lake Braddock students. And when I add these all up, 10, 15, 45, that's definitely not 100 students. So that means that we have, so 10 and 15, that's 25, 25 plus 45 is 70. 100 minus 70, we have 30 students that were surveyed that 1, aren't seniors, and 2, didn't choose virtual learning. We have 85 patients from a local hospital were surveyed. Here are the results. 50 of the patients surveyed were male, 20 of the patients surveyed were married, none of the patients surveyed were male and married. Okay, so our events are male and married. Since none of the patients surveyed are both, that is a mutually exclusive event. So that means that we have two circles here that should not be intersecting. So this is easy. If we have 20 patients that are married, we've got 50 patients who are male. We surveyed 85 patients, so that means that the 15 extra are not male and are not married. So let's talk about notation. So the first one is called the complement. So let's say we call this event A and event B. So I'm looking for the complement of A, which is another way of saying not A. So it would look like this. Here's A. The complement is not A. So I'm going to shade everything that's not A. So everything shaded is the complement of A. Here we have the complement of B. So we're talking about not B. So again, oops, we've got A, we've got B. Here's B. but I want the complement. So I don't want B, I want everything that's not B. So everything in my shading is not B. All right, our next word is intersection. We've already talked about that. So let's call this event A, and this is event B. If I'm looking for the intersection of A and B, I'm looking to see what do they have in common. So if I do my shading, if I do A and I do B, the only place where I see both colors, the only place that they have in common is right here. That is the intersection. Now for this one, if I do AB, all right, well, here's my A. Here's my B. Where do the two colors overlap? Nowhere. So when the intersection is 0, we call this mutually exclusive. Hopefully you've heard that enough now. So intersection means we're looking for where the two colors are overlapping. That shows us what those two events have in common. Our last one is union. So A union B. Okay, so union, if you think about it, a civil union is kind of like a marriage. So when you're putting things together, if you're uniting them, that means we're putting all of the pieces together. So if this is A, and this is B, I'm not interested in where the two colors are overlapping. I'm just interested in where everything is colored. So those two, all these pieces that are shaded would be the union. Another way that you can find the union is this formula right here. So basically it's taking all of A, adding all of B, and then subtracting that intersection because it's been counted twice. All right, here we have our mutually exclusive event. So same idea, if I put my pieces together, that means I would add whatever is shaded. I'm not interested in what they have in common. I want to add what they have together, or I want to add all of these shaded pieces together. So if you think about this formula right here that we just have above that finds union, we know that a mutually exclusive event like this doesn't have an intersection. So I could make this 0. Sorry. So then the probability would just be A minus, or A plus B. All right, so some practice with shading would look like this. Let's say that this is A and this is B, and we're going to use the same values for all of these. And for this one, I want to find the probability of just A. Well, the first thing I want to do is look at this Venn diagram and decide if it's completely filled in. It's almost all filled in. The only thing that's not filled in is the outside. So since these are decimals, that means that we want this whole sample space to equal 100%. We want it to equal 1. So far we have 0.3, 0.1, so that's 0.4, plus the other 0.4 makes this 0.8. That means that 0.2 is left over. All right, so I'm looking for the probability of A. So here's A. I'm going to shade all of A, and it looks like it's 0.3 plus 0.1. So the probability of A is 0.4. Let's do probability of B. So same thing, AB. And I don't want to forget about the complement, so like that. Okay, so this time I want to know probability of B. So I'm going to circle B, all of B. And it looks like that B total is 0.5. All right, so this time I'm going to do the intersection, which means I want to know what they have in common. So I'm going to start with A, taking all of A, and I'm going to combine it with B, but I am looking for where they are both shaded, and you can see that you have yellow and green right here. Okay, so same idea. I'm going to start with my A. And my B. Union means that I'm going to unite them. I'm going to put all the pieces together. So everything that's shaded, 0.3, 0.1, 0.4, for a total of 0.8. All right, we just got a couple more. We're going to take it up a notch. And if you remember, we had 0.2 over here. All right, so this time I want the probability that we're not going to get B. Okay, so here's B. But I don't want B, so I should be shaving everything else. So everything else shaded would be 0.2 plus 0.3. So it looks like the complement of B is 0.5. All right, so this time we're doing the complement of A and we're uniting it with B. So here's A. I don't want A, so I'm going to put everything out here. Forgot the 0.2 though, so I got to go back. All right, I'm uniting this with everything in B, so here's B. So unite means that I'm going to add all the pieces that are shaded. So I've got 0.2 shaded, I've got 0.1 shaded, and I have 0.4 shaded for a total of 0.7. Another way you could do this is you can tell that A is this little piece here is the only thing that's not shaded. So you could always do 0 or 1 minus 0.3 and you get the same thing. All right, this time I want to do the probability of A, intersect B. So I'm looking for A intersect B, but the complement. So this one's tough. So let me start with A intersect B. I know already that the intersection is right here, but I don't want that. I want everything else. So I'm really interested in all the rest of this. So two ways you could do it. You can add all the shaded pieces together. Or since you know that it's everything but the middle, you could do 1 minus 0.1 and get the same thing. All right, so for this problem, we're doing not A. So I'm going to highlight everything that's not A. So here's A. Here's everything that's not. And then not B. Okay, so here's B. And here's everything that's not. And I'm uniting them. I'm putting all of those shaded pieces together. So I see that point 2 is shaded. And I see that, oh, I messed up. I should have shaded this, right? Not B. All right, so I have point 2 shaded, I have point 3 shaded, I have point 4 shaded. So it looks like this is point 9 again. All right, so my last examples are pretty much the same thing, but we want to look at what happens when you don't have probabilities. So for example, if you have A and B, and this is 10, and this is 3, and this is 19, let's say this is 5. Right, so the probability of A, we know is going to be the whole circle of A. So all of this is A. So that's 10 plus 3, so that's 13. But that's not a probability, so we need to count up all of these. 10 plus 3 is 13, 13 plus 19 is 32, and 32 plus 5 is 37. So our probability is 13 out of 37. All right, same ideas for the rest. If you have whole numbers instead of probabilities or decimals or percentages, we just want to make sure that we're writing our probabilities out of the entire fraction. So, right, if you did probability of not B, that would be all of this is B, but we don't want that, so I'm going to shade everything else. So not B is 5 plus 10, that's 15, so the probability is 15 out of 37. All right, and we know that A and B, so all of A, all of B, we're uniting the pieces together, so we're counting up all the pieces. 10 plus 3 is 13, 13 plus 19 is 32. This is 32 out of 37. And a special note that when you're working with fractions, don't simplify them. Okay, you don't get points off on the AP exam for not simplifying. You get points off for simplifying incorrectly. Okay, so you're better off just leaving a fraction unsimplified than trying to simplify it and getting it wrong that way.